Welcome to Lesson 2B, Relative Humidity. We're going to discuss relative humidity, which is a measure of how much water vapor is in the air. So just think of water as a J, a contaminant. It's not really a contaminant, but it's just like any other species mixed with the air. By introduction, dry air means there's no water vapor or zero humidity. And so when you see this M-air molecular weight 28.97, that's for dry air. Moist air is air with some water vapor, but less than 100% relative humidity, not saturated. And then wet air is defined as air with 100% humidity. It's saturated with as much water vapor as it can hold. And of course, the molecular weight will change because it's a mixture of gases, one of which now is water vapor. The relative humidity is a ratio that has to lie between 0 and 100%. 0 for dry air, 100 for wet air, what we're calling wet or maximum wet air. So here's the formal definition of humidity. Humidity is, and we'll call this just the partial pressure. So I'm going to use H2O. Unless I'm lazy, sometimes I'll just put J, but we're talking about the water here, water vapor, which is an ideal gas. So humidity is the partial pressure of the H2O, where species J is the water. And then relative humidity, and by the way, we're going to use RH for convenience. Some books use phi, but there's too many variables to remember what they mean. So RH is easier to remember. Relative humidity is just the partial pressure, pH2O, over the maximum possible partial pressure, which we call either the vapor pressure or the saturation pressure. Now, the vapor pressure is what fluids people usually use. In a fluid mechanics book, they'll use PV. PSAT is what the thermo people usually use. So you'll find that if you look up this in a thermodynamics book. I will use the two interchangeably. So sometimes I'll use one, sometimes the other, depending on my mood, I guess. Where do we get these? We look up PV or PSAT in tables, and there's some online tables. They are also available on the website, which I'll show you in a second here. But PSAT is a function of temperature, or you can write TSAT is a function of pressure. So they're a function of each other. And generally, PSAT goes up as T goes up. So what does that mean? You can think of it this way. If you have a bigger saturation pressure or vapor pressure, saturation pressure, the air can hold more water vapor. So I'll just write that as a comment. Air holds more water or more humidity as T goes up. So let's look at the table, and I'll just put a comment here. See the table on the website. You can use other tables, but for consistency, especially with quizzes, use the same numbers as I use. Make sure you use the same table. So I want to show you that. You can click on links and references here, and that takes you to this reference page. And I guess the first one there is saturated water table. And so here's temperature in degrees C and PSAT in kPa. And so you see, for example, at normal room temperature around 20 degrees C, PSAT is 2.339 kPa. As temperature goes up, PSAT goes up. And so that's why we can say warm air can hold more moisture than cold air. Here's the definition of relative humidity in words. We say that it's the actual partial pressure of water vapor divided by the maximum possible partial pressure of water vapor, which is at the same temperature. And you can think of it as if it were saturated at the same temperature. So that's the two definitions in words. Now, just a quick example of this in Denver, which you know is called the Mile High City. So it's about a mile high in elevation. It turns out that its typical atmospheric pressure is only around 82 kPa compared to normal sea level is 101.325. So that's a lot lower pressure. And remember, PSAT is a function of temperature or vice versa. So you can have T as a function of pressure instead of P as a function of temperature. And so at this pressure, if you look at that table and you interpolate, you'll get that TSAT is approximately 94 degrees C. So that's the temperature at which water boils. So if you're up high on a mountain like in Denver, a mile high, water boils at about 94 degrees C instead of at 100 degrees C, which it does at sea level. So that's why you have to, say, boil a hard-boiled egg, you have to boil it longer in Denver than you do at the beach. And the opposite is a pressure cooker, which purposely makes the pressure high in the pot, and then that makes the boiling temperature higher. So you're boiling something at a higher temperature than 100 degrees if it's water that you're boiling. All right, let's do a couple quick examples here. It's a hot summer day. Temperature's 95 degrees, 35 degrees C. Pressure, more typical of around State College here, under 100 kPa. Relative humidity is 90%. So this is a hot, humid day. Remember, like in the summer when it's just so sticky and hot. So let's calculate the mole fraction of water vapor in the air. How much water vapor is actually in the air? So here's our equation for relative humidity. And let's look up first the saturation pressure. So that table I just showed you, we get 5.628 at 35 degrees C. Now we can calculate the relative humidity. So simply just plugging into this equation, solve this for pH2O, which is RH then times PVH2O or PSAT-H2O. We also know that Yj, or here YH2O, is PJ or pH2O over P, and that P is the atmospheric pressure. We got several pressures going on here. We got the PV, we got the P atmosphere, and we got the pH2O. There's three different pressures going on. So we combine these two and we can write then YH2O is equal to the relative humidity times PVH2O over P atmosphere. So that's our answer in variable form. And now let's plug in the numbers. So I plugged in the relative humidity, which is 90%, but notice that I made it as 0.9 instead of 90 times the saturation pressure or the vapor pressure, and then divided by atmospheric pressure, I get 0.050855. Multiply that by 10 to the 6th to get the ppm. So it's 5,900 to 3 significant digits ppm. So that would be our result. And just a couple comments here. Notice if you say how much water vapor is there in this air in this hot summer day. So it's approximately 5% by volume is H2O, water vapor. By volume or by mole fraction, that's the same thing, remember, because Yj is Vj over V, which means that about 5% of the molecules in this humid air are water vapor. The rest is air. But that 5% may not seem like a lot, but you can really feel the difference. And it turns out that the mole fraction of YCO2 is around 414 ppm in the atmosphere today. It's growing, as you know, whereas YH2O is here around 51,000 ppm. So you see that water vapor on a humid day is much, much greater than the amount of CO2 in the atmosphere. And just one final comment. I used to live in California, Los Angeles area, Pasadena, where it was usually very dry. So the air is like a desert climate, very dry. So 95 degrees Fahrenheit was not unusual in that part of the country. But since the relative humidity was so low, like 10 or 15%, it didn't feel as hot because it's not as humid. So humidity really bothers you. The reason for that is because it's harder for your body to cool you down by sweating. So that's why you feel hotter in a very humid environment. Okay, let's do another quick example. The same hot summer day, so it's 95 degrees, pressure's the same, relative humidity is the same. But now something happens, and that is that the temperature suddenly drops rapidly to 86 degrees or 30 degrees C, and the pressure also drops. So meteorologists would say a cold front has moved in. Calculate the new relative humidity of the water vapor in the air. Since the temperature changed, now I look up in the table a new PVH2O, which is now smaller than the previous one we had since the temperature has dropped. So if we assume here it's the same air, therefore the YH2O, this mole fraction, remember we talked about this last time, does not depend on T or P. So it should be the same. So we'll set H2O is the same as last time, which was 0.05, and I'll put in all my digits to be accurate here, 0.050855. And so RH, using this equation, is equal to PH2O over PVH2O times 100%, but this guy is equal to YH2O times P atmosphere, since remember Yj is Pj over P, and that P is P atmosphere. So that's going to be what we'll put in the numerator, and then we'll use our new PVH2O for that. And so when I plug in the numbers, I get 117.98% or roughly 118%.
But sir, that's greater than 100%. Isn't that impossible?
You're right, Ned. Remember, the relative humidity can only be between 0 and 100%. So this cannot be the right answer. The air at this temperature cannot hold that much water. So what will happen? It will rain. This is how meteorologists actually can predict rain. They say, well, the temperature is going to drop, the pressure is going to drop. They do this kind of calculation and say, oh, relative humidity, if we kept that much moisture in the air, it would be 118%. And red flag, that can't work. So therefore, it will rain. That's the incorrect answer. The correct answer is that RH is 100%, because that's the max. And so what will happen is some of that water vapor will condense into little droplets that become rain droplets, and that's why we say it will rain. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.